Scalar T, micro and macro optimization, used with D88 Data Research Library. What do I mean by scalar? Just a note, everything in this presentation is an unsigned integer. We are not dealing with any negative numbers. This is not a big integer library either. CPU hardware implements numbers of a fixed size. They can't go any bigger. Bigger numbers must be simulated from these smaller fixed size numbers. These are scalar integers. For example, we have a char which is 8 bits, a short is 16, an int is 32, and a long is 64. Why not bigger? Will there ever be a 128-bit computer? I don't think so. It's really not needed. So what is the Scalar T library and why do I need it? Consider the following. Imagine a matrix transformation. The complexity of a matrix transformation requires us to compute n times n elements. So as we increase the complexity of our base polynomial, our matrix complexity grows exponentially. Most matrix transformations will use the multiply accumulate operation. D88 uses a standard multiply accumulate and also a custom multiply 3 times inverse add instruction. As we grow our bit coverage by increasing the size of our polynomial, the complexity increases exponentially. The Scalar T library is useful because the complexity of scalar multiplication increases at half the rate as the matrix transformations. What this means is that as the complexity of our polynomial grows, at some point, it will benefit us to use a synthetic scalar instead of the maximum register size of the CPU. This works because approximately half of the complexity of multiplication can be ignored when we're not implementing a big integer. These empty blocks represent work that would be done by a big integer, but are not needed with a scalar. We can increase performance by using smaller polynomials and larger integers. Let's look at how this problem lays out in memory. If we are using 4 64-bit integers to give us 256 bits of algorithm coverage, we will need to combine these with a cubic complexity polynomial. If we have a 128-bit integer, we can do the same with linear complexity. Since D88 is only interested in bit coverage and not other factors, this works out very well. D88 can use very large polynomials with its elective field symmetry. It also can use scalars of any size, unlike many applications which use fixed 8-bit scalars. There's a point where a polynomial becomes so complex that a synthetic scalar is actually faster than native CPU integer units. This is our macro optimization. We've looked at the problem as a whole and discovered a way we can do it better. Moving on. Here we have a multiply accumulate operation. It represents a very small memory and cache profile, meaning it'll run very quickly. It'll perform very well. Consider the same multiply accumulate, but with a 512-bit scalar integer. This has a very large memory and cache profile if we perform the operations monolithically. However, if we implement a variation of this multiply accumulate, which actually streams across the data, we can achieve optimal cache access. Doing this dramatically increases the performance of our synthetic scalar and allows it to become part of our strategy when dealing with large polynomials and large bit coverages. This is our micro optimization. For illustration purposes, here is an implementation of a finite vector multiplication. It works by moving the resultant multiplication into a new scalar integer. Here is a similar algorithm, but it is in-place multiplication. It is slightly more complicated. However, the performance at larger scalar integer sizes goes up. I thoroughly enjoyed writing the Scalar T library because it's a dramatic example of when optimization is appropriate, when it's appropriate to delve into complexity and embrace it. And normally code, like what you're about to see, would be reserved for, I don't know, processor architects and microcode engineers. I was thoroughly excited when I discovered that, hey, the complexity of scalar multiplication is half that of a matrix transformation. Therefore, I have a reason to optimize a scalar integer. Here it is, a fused vector multiplication with an inverse add. It's a beast, but it's beautiful. Go ahead and pause the video if you want to take a look, or the source code is online. This is an open source project. The link will be at the end of the video. As a software craftsman, I have to lament how infrequent it is that we get to exercise our algorithm muscles and do something awesome like this. I'm quite proud of this work. The last function increases the performance over the first by about 50%. I'm also working on a fuse in place multiply 3 invert add. It'll increase the performance by 50% again. Remember, the key to optimization is understanding our memory profile and minimizing the amount of memory we work with at any one given time. Take a look at the open source project. While you're there, you might want to look for the following. A 16K chunk of data computed with a 1024-bit scalar and a 128-degree polynomial can be completed in about 25,000 milliseconds for several thousand iterations. The same data chunk, but computed with a 64-bit scalar and a 2048-degree polynomial, takes almost 45,000 milliseconds for the same amount of iterations. Keep in mind that the application of this matrix isn't sensitive to the scalar size or the polynomial size, only the bit coverage. Did we really just beat native integer performance with a synthetic scalar and have room to optimize still? Yes, we did. We did this by paying attention to macro and micro optimizations and designing an algorithm to blend them. And there's more to come.